Okay, folks, thank you for being here today. We have the pleasure to have Jessy Lin and Nicholas Tomlin presenting their paper on decision-oriented dialogue for human AI collaboration. Jessy is a rising fourth-year PhD student at Berkeley, advised by Dan Klein and Anka Dragan, and her research focuses on building AI agents that use language to collaborate with people and learn from human feedback. And Nicholas is a rising fifth-year PhD student at Berkeley Electrical Engineer and CS department, advised by Dan Klein, and is also part of the Berkeley NLP group, where his primary line of research focuses on language grounding and pragmatics, especially in gameplay domains. He has also worked on computer crossword solving, historical language reconstruction, and interfaces for language documentation, and is currently an instructor for the famous Berkeley CS 188 Introduction to Artificial Intelligence class, and where we are really glad to have them here. And Jessy, you can take the lead.
Yeah, thanks for the introduction. So we'll be talking about our paper that we did in collaboration with Jacob Andreas and Jason Eisner at Microsoft Semantic Machines. Cool, so let's get started. Great, so let's talk about what assisting humans looks like in the age of LLMs. So now that we have these like amazing, language generation machines, a lot of questions that used to be hard are now easy. So factual questions, let's say like, how much did the NVIDIA stock rise this year, are now really easy to answer if I wanted to know that for some reason. On the other hand, questions that require more difficult reasoning abilities, like let's say, I want to plan our company's Q4 strategy, can we look at the financial reports and market analysis with an LLM and figure out together what we need to prioritize before the end of the year? Now, questions like these that require some kind of real-world reasoning under uncertainty are still hard. And similarly, like a lot of questions are easy, even if they require things like external tools, things like, can you book a flight for me? We can imagine like ChatGPT can hook into some API and book an arbitrary flight for me. But figuring out like how to navigate the preferences and constraints that I have when booking a flight for an entire company team, everyone has their individual preferences. We have to mediate them and figure out the best set of flights for all of us. That's still hard. And again, like LLMs are somewhat lacking in being able to reason about complex preferences. And again, similarly, questions like, my internet stopped working. Can you generate a list of things that could be going wrong here? That's easy, but what's hard is figuring out how to collaborate with a human to troubleshoot what might be going wrong step by step. Let's say if I were to call up like the customer service and be able to walk through some of the assistance steps to resolve this problem. So here we're missing some kind of collaborative abilities. So these are the kinds of things that ideally in the long term, we want intelligent agents to be able to help us to do. But right now, LLMs are lacking in these areas. So this motivated our development of a new set of tasks that we call decision-oriented dialogue that are centered around tasks like these, where we want LLMs to help people make decisions. So people make all kinds of decisions in everyday life. It could be planning a trip, putting together a desktop computer and figuring out what parts fit together, diagnosing patients as a doctor, choosing what to invest in, mediating group decisions on where to eat at a restaurant, or collaborating to decide on the best course of action. And in all of these situations, we'd like language agents to be able to help us make decisions. So in this paper, we developed 3 domains where we can sort of model agents as helping humans in some realistic domains. So we'll start with the first one that we call optimization. And this models a scenario where you and let's say another area chair for a conference are trying to collaborate to figure out how to match papers to conference reviewers. And maybe I know some things about what papers might be suitable for certain people, and the other AC knows some information as well. And we might chat in dialogue to figure out what the best matching would be if we shared all our information. So here we can imagine that an LLM agent in the long term would be able to serve as one of the collaborators in this scenario, where maybe a large language model or computer has access to a big database of preferences. And I, as a human, have knowledge that's maybe more up to date or more hard to encode in databases in this like rigorous way, but nevertheless, like our preferences that should be taken into account. So the second setting is planning, which, as I mentioned, like people plan trips all the time. And this is a situation where we can imagine collaboration is needed to figure out the best itinerary that a user would enjoy. So here, the information is asymmetric. So as a human, I know what I like, what I prefer when I travel. And as an agent, like whether it's a human travel agent or an LLM agent, might have access to a database of sites that I could visit, features, ratings, and things like this. And again, we have to collaborate in dialogue to figure out what the best itinerary is if we, aggregate or integrate the information between the preferences that I know and the information about the world that the agent knows. And finally, as a third domain in our suite of benchmarks, we have mediation, which is a multi-party dialogue setting where there's two people or more than one person talking to an agent that's trying to mediate between the preferences of the group. So here, there's a scenario where we're all trying to book a set of flights that maybe arrive around the same time or satisfy some constraints among the group, but everyone has their own individual constraints for what flights they prefer or can afford, and individual constraints about when they can make those flights. So again, the agent here is serving to mediate between the preferences of the group in order to arrive at a group decision that can satisfy everyone's preferences. And we'll communicate in dialogue to figure this out. So to give a sense of how our dialogue tasks fit in, the kind of dialogue tasks that exist today, typically when you hear about like goal-oriented or task-oriented dialogue, you get dialogues like these. This is from Air Dialogue, where there's still some goal where the travel agent has to help a customer book a flight, but it's a lot more simple in the kind of collaboration that you need. So you can see the agent here asking questions like, what's your connection? The customer answers, I want a direct flight. The agent asks, is there a preference for the class? The customer answers no. So it's very much a sort of like information gathering sort of collaboration dialogue. Whereas in our tasks, there's a lot more complex preferences that you have to navigate in order to figure out, okay, like given your preferences and given what's available, here's a solution that might be the best combining that information. Whereas tasks like Air Dialogue or other task-oriented dialogue, while they share the same goal, maybe have a more like flowchart kind of reasoning in determining what the best solution might be. And now that we have LLMs that can ask a lot of these questions and reach the basic level of language understanding to like ask some of the right questions, we want to start moving towards the more complex collaborative behaviors that we might see in the tasks that we develop, as well as the suite of multi-agent cooperative tasks that maybe a lot of people in this group are interested in, things like Hanabi, Overcooked, or Diplomacy, where people are really exhibiting really complex collaborative behaviors like signaling or trying to like strategically communicate information in diplomacy to build like alliances and things like this. So when we were building this suite of tasks, we were pretty inspired by a lot of these multi-agent tasks that study really rich collaborative behaviors. And we wanted to bring some of language into these ideas. Cool, so let's go into more depth about how we build these tasks and both what human collaboration might look like, as well as what it might look like to build agents that operate in these settings. So to start off, we collected human-human dialogue data by building a set of interfaces for each of these tasks. So we collected hundreds of games from both mTurkers and internal data specialists. The dialogues are pretty long and exhibit a lot of interesting collaborative behaviors, and we'll go into some of that later in this talk. So first, for optimization, I think it helps to look at maybe as a participant in this dialogue, what kind of information would you have and what kind of behaviors would you, or what kind of information would you start to reason over? So again, the task here is to figure out the best matching of reviewers to papers. So what you have in terms of information is a sort of spreadsheet of like affinities or matchings between reviewers on the rows here and papers on the columns. And each person, so there's two people in this dialogue, each of them has a partial view over all the values in the table. So I might not know like, Ava's preference for the fourth paper, but I know some subset of values in this table. My partner knows a subset, and we have to figure out how to like pool our information or figure out which pieces of information to communicate in order to reach the best solution. So at the end of the dialogue, what we're going to do is, after we've talked for a while, we'll decide on a proposal, which is a matching of reviewers to papers. Also, feel free to interrupt with questions at any point or comments. Cool. So in the second task, we have planning. So we have the user view on the left here and the assistant view on the right. In the user view, what you see is your preferences, which we generate from some underlying parameters, but then show to the user in the form of natural language. So a lot of what we thought about in the course of task design was how to give users or human participants their preferences so that we could evaluate the ground truth of like, how well did a certain proposal satisfy their preferences, which, ideally in the, real version of this task, you would have someone's real preferences which live in their head. But for the purposes of evaluation, we want to figure out, how well our model is actually optimizing for the preferences that people have. So we generate the preferences and we present them to the user in the form of natural language so that they, it kind of represents the preferences in a more natural way, as opposed to like, oh, I like French food with a value of 5, which maybe leads to unnatural dialogues. So this kind of document that you see in the left-hand corner here is an example of what you might see as a user participating in this dialogue. Now, on the assistant side, they don't get to see the user's preferences, but what they do see is a map of all the locations that are available. And each location has a set of features, which is randomly generated on every dialogue. So as an assistant, as you receive information from a user, you can start to query some of the values or the sites and figure out, okay, maybe this place is a suitable location for the user to visit first, and then send over proposals. And when you send over proposals, you can see on the user side that they see the list of proposals or see the list of events that you've proposed and how they feel about them. So based on their preferences, you can see, Saul's is a pretty good place for them to go given their preferences. There's some travel distance maybe in between that's not preferable. And overall, you get some like overall reward for the dialogue based on what's proposed and the user's underlying preferences. So again, the goal of this game is for the user and the assistant to collaborate in dialogue, for each of them to communicate their preferences or what's available out there in terms of like the locations and the features in order to arrive at the best 3-event itinerary. And then finally, for the mediation task, here again, the goal is to schedule a set of flights that matches some group constraint of arriving at the same time, while also individual constraints about like not missing certain calendar events. So each of 2 users in this case, has a list of calendar events. And what's private to them is how important each of those events is. So I might say like, the meeting on Friday can't be canceled. And I really strongly prefer that the flight that we book doesn't conflict with that event. Now, the assistant has access to the calendars, but they don't have access to those event importances. And they maybe also don't have access to some private events as well. But they can see all the users' flights. They can see all the users' calendar events, or some of the users' calendar events. And then they can start to collaborate on, the assistant can propose, maybe we want to try for a flight on Wednesday. And then the user can say, oh, that's strongly not preferred because of, these events that I have. And maybe we can do something on Thursday. And so the dialogue proceeds like that. Cool. So are there any questions at this point about what the tasks are from a human perspective? Cool. Yeah, go for it.
I have a question about this one. So this is kind of like a back and forth between the agent and the users that have defined preferences in their calendar. is there any reason why you can't just like do an optimization algorithm on everyone's calendar here?
Yeah, you totally could if you had access to all the information. But as the assistant, because you don't know the private preferences or you don't have access to some events, you can't optimize from the initial step. You have to start collecting information, and then maybe like not all the information is going to be shared in the course of the dialogue. So you're kind of operating in this partial information setting.
Okay, so you don't have access to everyone's calendars. It's just kind of like the agent makes a suggestion and then they kind of like update their state or like known information about everyone's calendars, and then they just kind of like ping each other on that. Okay. Got it.
Yeah, so the assistant has access to some events, but not all of them. So you have a sense of like, maybe here are some initial proposals that might be good. But yeah, you can't reach the optimal solution immediately.
Okay, thanks.
Yep, or? Oh, or do you have a question?
Yeah, sorry, am I unmuted?
Oh, no, you're good now.
Oh, okay, good. Yeah, I was wondering, so it looks like there's this calendar widget in this like UI, and that's for these temporal constraints. Were there other constraints you were looking at, or is it just mostly calendar?
Yeah, for this event, for this task, there's also the group constraint of wanting the flights to arrive around the same time, and then a like budget constraint. So in all of these tasks, there's like some set of like features basically in the reward function, and the overall score that you get is a combination of all of these features. So yeah, there's some other preferences in this case beyond just the calendar preference.
And for example, for the arriving at the same time constraint, that one isn't represented directly by like a piece of the UI. It's like underlying somewhere in the text, basically.
Yeah, so you will see like when you propose a set of flights, you can see on the scorecard, it might be a bit small, but you can see a value for how well that preference is satisfied. But as a user, you don't really have access to that. Just like, I don't have a number in my head for how much I want my flight to arrive around the same time, but I can say for a particular set of flights, oh, that's a bit too far apart. Like I would prefer it to be closer together. So there's a lot of details in like maybe how we designed the tasks that, yeah, we don't have the chance to go over here, but a lot of this was aimed around like realism of the dialogues and like trying to get us close to the setting where I have preferences in my head and I want to communicate them to an agent.
Yeah. Great. Thank you.
Thanks. Cool. So yeah, so now we've talked about the human interfaces for each of these tasks. And again, the ultimate goal is to build agents that can assist humans in these tasks. So you can imagine in each of these settings, there's an assistant or one party that would be replaced by a language model that would have access to the same information, but obviously, yeah, collaborate in the same way as human-human teams are doing. Cool. So just to talk a little bit about the underlying structure in these tasks. So in our paper, we talk a little bit about how to formalize the set of tasks. So, so far I've presented it in a more like intuitive way, but you can start to see commonalities between the structure of, let's say, the reward function and the things that you need to infer in each of these tasks. And so if we were to, formalize what all these tasks share in common, the goal here is to make a decision, which we can see as a graph selection problem. So you can think of this as like, each of the nodes here is, let's say, a location, and the edges are like distances between them. And I want to pick a subset of locations. So each of the nodes and each of the edges has a weight. So maybe I prefer certain events, or the weights on edges are higher than others. And so I want to make a decision that maximizes some reward function, where the function is over the features of the nodes and the vertices in the graph. And then in each of these settings, there's some reward function theta, which is the same as the reward function that we typically have in let's say like other settings or like multi-agent settings, where theta represents like the preferences over each of these features. Cool. So, you know, in our baselines, we don't necessarily use this graph structure. A lot of, or all of our baselines are prompting-based baselines. But it's interesting to think about the structure that's shared among these tasks because it does enable the potential for structured methods that maybe, let's say, do explicit probabilistic inference over the values of the nodes and edges. And it also enables like potentially analysis of, you know, like here's the value information of inferring the value of this node or this edge. So we sort of formalize the set of tasks with like future applications in mind, even though the baselines that we'll present soon don't use this structure yet. Cool. So again, like as an example, in the planning task, the nodes would be locations. The weights of the vertices would be the location features and how they interact with the reward. And then the edge weights would be distances. So the reward features would be something like, you know, I have a really negative weight on distance, so I don't really want to travel too far, but I really want to visit like these particular nodes, and that would be represented in entries of your theta vector. Cool. So we present these visual UIs to humans, but for agents, we're going to translate this information to text, and all agents are going to get the same information that we present in the UI, but in the form of text. So instead of that list of flights and calendar events, you're just going to get that as a table. And then you're going to begin to chat and say, you know, user one said this, you as the agent to user one, and then generate from, let's say, like a LLM from there. And then as the dialogue proceeds, at the end of the dialogue, an agent will make a special message, which is a proposal, and that proposal will be scored to generate a reward. So depending on, you know, how well the proposal satisfies the user's preferences. So the environments have some nice features for RL, which again, we don't do in our baselines, but could be good to do in future modeling methods. So one, they're procedurally generated. So unlike previous dialogue tasks where you have some supervised data set and you train on that and then you evaluate on some test set, all of the environment instances here are generated automatically. So we randomly generate all the locations, we randomly generate all the preferences, we randomly generate all of the features of the locations, and this makes it so that on every reset or on every new dialogue, you have a different set of preferences. And to actually succeed on all the instances of the dialogue, you do have to do some sort of general reasoning. Secondly, you might notice that the reward is not just sparse, but it's a continuous value between 0 and 1. And because it's determined based on how the user's preferences are satisfied by the proposal, you can think of it as a more fine-grained reward for communication success. So as opposed to just like 1 for booking the right flight or 0 for not booking the right flight, the better agents are able to elicit information from people and reason over that information, the higher the reward will be. And then finally, as an advantage, like a lot of these domains were, we thought a lot about like what are some realistic or useful domains where agents could actually assist humans. And, presumably like if you build an agent that succeeds on the planning part of the dial-up environments, then it's a real step towards, agents that can do the same thing in the corresponding real-world domain. So I'll pause. Oh, yep. Question from Dave.
Yeah, sorry, I was trying to anticipate the pause there.
Yeah.
So you mentioned this second point about the reward, like, and how it basically like it's between 0 and 1, where 1 say is like the most successful you could get at a task. Is there any notion of like how long the communication takes to extract information? Like, because you might imagine like in the limit, you just ask every question possible and then you end up with like all of the information. But
yeah, for sure.
Yeah.
So the real goal would be to maximize the reward of the proposal while minimizing communication cost. And I think the thing that we end up doing in our results, as we'll soon show, is to plot basically like a Pareto like frontier of for a given communication budget, like what's the reward that a model or a human gets? So as opposed to like combining them all into one reward with like some weight. So I think that's probably the best way to kind of interpret results on this benchmark. So to think about, yeah, for a given budget, what's the success of the proposal?
Okay, thanks.
Cool. So I'll pass it off to Nick at this point to talk about evaluation.
All right, sounds good. So I'm gonna start screen sharing now. Can people tell me if they can see my slides? All of your faces have vanished, so you're gonna have to speak out loud.
Yeah, it works well.
Yeah.
Okay, great. Cool. So we've talked to the tasks, we've talked to the environments. Now we're going to talk about evaluation. We're going to be evaluating language models on the suite of tasks. For this paper, we're focused on task design and benchmarking based language models. So the models that we evaluate are going to be relatively simple. They're going to be language models of the like of ChatGPT or GPT-4 with only some basic modifications, some basic tool use that allows them to cram all of this information about events and preferences and things like that into their context window. But for the most part, you should think that we're evaluating base language models here. If you have more questions about how that tool use works, we can come back to that at the end. So how do we evaluate these models? Well, the gold standard, the thing that we ultimately want to do, is to figure out whether these models are good at assisting real human users at the suite of tasks and other tasks like these. So that's human LM evaluation. However, as with many other tasks in NLP, this is expensive, but for this suite of tasks, human LM evaluation is especially expensive. On the data collection slide we showed earlier, we pointed out that these dialogues between pairs of humans can often take 10 or more minutes per dialogue just to make one decision. So if you want to evaluate your language models in collaboration with humans, then that starts to get very expensive. And if you want to, say, use those dialogues as an auxiliary training reward, then it gets really expensive because these are long dialogues and human eval takes quite a while. So in this paper, we're not going to do human evaluation. Instead, we're going to look at some proxy evaluations. And the first obvious proxy that you might think of is something like self-play. So in self-play, instead of having one language model that we're evaluating, we're going to have two. One is going to be an assistant, and one is going to be a user simulator. So we have three different tasks. In the first task, the reviewer matching optimization task, the setup is basically symmetric. So this user simulator and assistant end up being roughly the same agent. They have the same prompts and the same conditioning information. However, in the other two tasks, we have different prompts and different set of tools that the user and assistant language models can access. However, as many of you are undoubtedly aware, self-play comes with a lot of drawbacks, especially in language settings. So for our tasks, we find that self-play can lead to really repetitive dialogues. It can lead to hallucinations, where these hallucinations then cascade over the course of the dialogue, where you maybe make just one mistake early on, and then these mistakes pile up as the dialogue continues. It also leads to only a partial exploration of the subspace of strategies that real humans might use when interacting with assistants. If the LM user simulator is not sufficiently diverse in its approach, then we don't get a good signal of whether our assistant is actually doing a good job of this task. On the bright side, it's cheap. It's easy to run this over and over again. It's easy to use this for iteration, but it does come with a lot of drawbacks. So to bridge the gap between these two evaluation methods, between human evaluation and self-play, we introduced this new evaluation method, which we call prompted self-play. In prompted self-play, we're going to take a partial dialogue that comes from a pair of humans and then ask LMs to continue that in self-play. So you can think of this as like doing dialogue rollouts after a partial human dialogue. And the motivation here is twofold. One, this is going to introduce some information into the context, which forces the language model or biases the language model towards staying on track. We're going to have some information being passed back and forth between these two human users, which should hopefully give the language models in self-play a signal about what to talk about and how this game works. Additionally, this is going to provide some basic information from the two players' perspectives. So in the itinerary planning task, for instance, this human-human prefix is going to it's going to already contain some information about the user's preferences, which the language models can then condition on when they go to complete the dialogue. So this functions as kind of an in-between between self-play evaluation and human evaluation. And we're going to use the human-human data that we collected earlier in this talk to serve as prefixes for prompted self-play. So we're going to talk through results for self-play and prompted self-play, and then I'll show some example dialogues as well. But before I show the example dialogues, let's look at some charts. I'm going to walk through these slowly because there's a lot of information in these results. This first figure is comparing our self-play results between pairs of language models for all three tasks to the performance of humans in collaboration with humans. So here you see 3 scattered plots. Each point in a scattered plot represents a single game, that is a single dialogue and decision that is made either by a pair of language models, that's the orange dots here, or a pair of humans, that's the red dots. We have 2 features. On the x-axis, we have the number of words, that's the length of the dialogue. And on the y-axis, we have normalized reward on a scale from 0 to 1. And what we see here for all 3 tasks, but especially for planning and mediation, is that these human dialogues tend to be significantly shorter than the self-play dialogues. So you see the red points are shifted more to the left than the orange points. There's a histogram at the top, which also summarizes this information in a way that might be slightly easier to see. But this suggests that humans are, in general, being more efficient with how they pass information back and forth when communicating about their preferences and constraints in these tasks. This is consistent with the intuition that I mentioned earlier that language models might be repetitive, or they might hallucinate, or they might just share unnecessary information, at least in the self-play setting. At the same time, though, it seems like humans are actually doing much better than language models at these tasks. So despite sharing less information, their scores are in general higher. That's indicated by these red dots being higher on the y-axis than the orange dots. So you'll see for most of these tasks, humans are achieving somewhere between 90 to 100% of the maximum reward, whereas language models in self-play are achieving slightly above what a random baseline would get. So in planning and mediation, you see this random baseline that comes from taking a random decision at the task. And most of the orange dots are above that, but they're not too far above that. In the optimization task, it seems like they're more centered around this random baseline. So that's humans versus language models in self-play. That's our first evaluation method. The takeaway here again is just that humans have shorter dialogues, but still manage to achieve higher scores. Now let's talk about prompted self-play. One thing that I didn't mention when I showed that visual about prompted self-play is that whenever we take this human-human dialogue prefix, a nice feature of prompted self-play is that you can actually tune how much prompting you're doing by either taking a shorter or longer prefix. So here we actually have 3 prompted self-play conditions instead of 1. So We still have our self-play results and our human results plotted on the far left and far right of this graph for context, but then we have 3 prompted self-play results in the middle. These are indicated by the 50, 75%, and proposal conditions, respectively. So what do these mean? Well, in the 50% condition, we're going to take an existing human-human dialogue and then chop off the first 50% of it. Or sorry, we're going to chop off the last 50% of it and then ask a language model to continue that dialogue, which starts with 50% of a human-human dialogue. In the 75% condition, we're going to start with 75% of a human-human dialogue and ask a language model to finish it. And in the proposal condition, we're going to take an entire human-human dialogue and remove only the final decision. So we keep all of the dialogue and we remove that proposal step at the very end. And then we ask a language model to, conditioned on this human-human dialogue, make a final proposal. So those are the conditions here. Now let me walk through some of the results. So in the optimization setting, that's the reviewer matching game, we actually find that models across the board fail to perform well at this task. So whether you're in self-play or prompted self-play, it seems like models just aren't capable of making a decision that's even better than random guessing. They're not getting anywhere close to human performance at this task, and prefixing the dialogue with a large amount of human-human dialogue doesn't seem to help. So one way you could interpret this is that models might fail to share information that's necessary for solving this task, but they also fail to condition on the information that's necessary to solve this task. So in this proposal condition, this prompted self-play with the largest prefix, the human dialogue already shares all of the information that's needed to make a good decision. However, the models in self-play fail to correctly condition on that to make a good proposed final decision at the end of the dialogue. And as a result, they achieve some score that's between 55 and 60% of the maximum reward. We see a somewhat similar trend in this mediation flight booking game. Scores for self-play and prompted self-play aren't that different, although there's a slight difference between the proposal condition and the 50 and 75% conditions. However, across the board, these models perform much better than a random chance baseline. That is, it seems like language models in self-play on this mediation task are capable of sharing some of the necessary information they need to complete this task. They're capable of sharing their preferences and converging on some final decision, which, although not perfect, is significantly better than random chance. However, I think the most interesting plot to me here is the one in the middle. It's the results for this itinerary planning task. Here we see that the amount of dialogue that you include in the prefix is directly correlated with the final score of the model. So in self-play, language models don't do a great job of this task. They outperform a random baseline, but still only achieve around 60 to 65% of the max score. But if you prefix models with a partial human-human dialogue, then they achieve 65 or 70 or 75% of the max score. So we still find that they're not performing quite as well as humans, which means that they're not making the optimal decision given the full dialogue history. But this also suggests that language models aren't as good at sharing the relevant information for this task as humans are. It seems like models that condition on human dialogues are outperforming models which just converse with each other in self-play. So those are the results for self-play and prompted self-play. Now let me show you some example dialogues just to give some intuitions for what's going on here. So let's look at a self-play dialogue first, and then we'll look at a human dialogue. So here's a self-play dialogue between two agents. Both are some GPT 3.5 system, and the user simulator goes first. And it says, I'm looking for some places good for groups of 7 with vegetarian options, a shop, takeout, Harper and Rye, rated above 3 stars, no live music, my budget's $70. Here, it seems like this user assistant is just dumping all of its preferences directly into the chat. This is probably not something that human users would be capable of doing in regular dialogue, so it's a bit unnatural. The assistant agent then says, I've got several options available. Do you have a price point? And you'll notice this is almost an immediate hallucination. The model's asking about a price point, even though the user simulator already stated its budget. So model queries for already revealed information. The user simulator repeats that information and says, if it's 70 or under, it's fine. And then the assistant makes a proposal. So here are the proposals of a few restaurants, and it provides a description of the proposal. It says, I found several options. All of these places are within a mile of each other. All have vegetarian options. Do you have other preferences? Unfortunately, it turns out these places are not all within a mile of each other and don't all have vegetarian options. So it's not a great proposal, and it's, again, hallucinating some information. The user simulator rejects this, seeing that it only scores 64% of the max score. And then the dialogue goes on for a bit longer. But in the end, this dialogue reached 65% of the max score, which is not great for this task. So that's only a partial dialogue. It's hard to go through the full things. If you want the full example of this dialogue, you can check out our paper. We have it in a figure. Let's look at what human dialogue is like, though. So here's an example. We've got two humans conversing with one another, and the user says, hey, I'd like to plan a trip. I want to visit touristy places, maybe a landmark, some places with Wi-Fi. Maybe they give some justifications for their preferences. But it's probably not all of their preferences, right? It's just a partial list of things that that human cares about. The human assistant then says, okay, here's a famous landmark. It's in walking distance to this coffee shop, and this coffee shop has Wi-Fi. And here's a partial proposal for a set of places that you might want to visit. Note, this is a partial proposal, not a full one. They only list 2 out of 3 places and then have a null option. They provide some reasons why it might be a good proposal, and then the dialogue continues. So the user then says, that looks good. Could we add another place? I want to go there. And the assistant says, oh, that's great. Here's a new schedule. It makes a proposal. The dialogue continues a little while longer. But here you can see humans are really like incrementally building up towards a good decision to this problem. And in the end, I believe they achieved a max score of, or they achieved 95% of the max score in this dialogue. So humans did much better than the language models did in self-play. And the question we want to leave you with is, how do you bridge that gap? How do you build models which have dialogues which look more like this one and less like the previous one? So this is an open question for us. It's future work, but we can hint at some potential approaches for modeling these types of complicated decision problems in dialogue. So the obvious thing you might think is that all of these tasks have some objective reward function. So you might just do some end-to-end reinforcement learning based on the task reward in self-play. There might also be more nuanced approaches where you do some like decoupling from between planning and language, maybe with some like latent policy induction. And then there are more structured approaches as well, where you take in the language from a user, parse it with a semantic parser or a PPL or something like that into some explicit belief state representation, and then condition on that explicit belief state representation. For all of these approaches, there are a bunch of open questions like, how can we or should we leverage the human data that we've collected for these tasks? Can the underlying task structure be useful? And how can we build models which learn behavior, not just for these 3 tasks, but for complicated decision problems in general? Long term, I think it would be really interesting to build models that can solve not just these tasks, but hundreds or thousands or just complicated decision problems in general. And you can think of this as being kind of similar to instruction tuning or RLHF, where in instruction tuning, people have built dozens or hundreds of tasks, which they use as fine-tuning for language models. And I think a long-term goal for this project might be to build a similar set of tasks for complicated decision problems, and then fine tune on that in one of these ways. So I believe that's it for us. Looks like we have approximately 10 minutes for questions. I'll go ahead and stop sharing for now, though.
Yeah, thank you both for a great talk. Does anybody have any questions for Jessy? And okay, Daniel. Yeah, go ahead.
Thanks. Yeah, this is awesome work. I'm hoping to convince some students to work on these data sets soon, and really well presented too. I was wondering if you had thoughts on whether there's room for like a cognitive load as an evaluation metric of some sort, like I guess like the length of the dialogue kind of gets at communicative efficiency, but and the examples you showed at the end about, you know, like incrementally revealing information kind of get at this too. But like, what would be, is there a right way, or what would be the right way to kind of like think about the burden on the person, maybe from turn to turn? Part of the reason I'm asking about the reviewer asked us about this just recently for another task.
Yeah,
But I
totally.
was just
Yeah,
curious.
I think that's a great question and something we've talked about a lot, actually, because all of these tasks have some complicated underlying optimization problem. It's certainly possible that you have some like high cognitive load task for users to do here, and hopefully that optimization would be offloaded onto the model, right? Like, hopefully your model isn't saying things that require the human to solve a CSP in their head. I think this is like partially addressed just by human evaluation. If you're doing human eval, then humans aren't going to actually put in the maximum effort into solving these tasks, and you'll see that methods with a lower cognitive load requirements perform better in general. But in terms of like automatic evaluation for cognitive load, I'm a bit less sure. I don't know if Jessy has thoughts.
Yeah, I feel like time is sort of a proxy, maybe. Of course, you can't measure LM because the generation is much faster or at a different time scale than humans, but definitely human versus human LM. You would think that at some point, like collaborating with computers would like decrease the time that it takes to solve these problems. So I think that's something that we definitely thought about as like another evaluation metric for the task.
Cool, thanks. Makes sense.
Thanks. Yeah.
Dave?
Yeah, thanks. Thanks for the great talk. I'm gonna kind of discuss one of your like open problems, I guess, which is like the whole thing about self-play. And at least like it's not super clear to me why self-play would ever converge in settings like this, because I realize it's not like traditional like AlphaGo style self-play. But in terms of like getting self-play to actually explore the strategy space and then improve, you need some sort of zero sum assumption. Like that's why it works in AlphaGo, is because it's they have the zero sum assumption, and like in AlphaStar and stuff. I think like what would be more beneficial, and you guys kind of touched on it with the whole diplomacy thing. Like if you look at Cicero, like the fair diplomacy agent, like they didn't use self-play because it's not a zero-sum game. And so what they ended up doing was like some planning based, some like mixture between like a planner and RL optimization, and then that kind of kicked out into the whole language model thing. But in terms of like planning next moves and planning what it was trying to do, it leveraged like an actual planning model. I think maybe that might be better for what you guys are trying to do in terms of like steering it into different directions and making sure that it stays like actually, I know grounded is like a term in NLP, but like making sure that it actually is going somewhere that you want it to go, because I don't think self-play will end up doing that here. Just a comment, I guess, but I think that looking at the actual Cicero training loop might actually be helpful for you guys here.
Yeah, thanks. I think that's helpful. I think figuring out how to build either explicit planning or belief inference tools in a general way is definitely still a thing that we're thinking about. Like, I think it's easier to imagine how to do that for one of these 3 tasks specifically, or for all 3 of them. But whether or not that method would generalize to these types of complex decision problems in general still seems unclear to me. I agree with the point about self-play, though.
Yeah, I mean, even if you look at like an exit style Monte Carlo tree search, like if you have one agent do that, like the agent that is the user, I guess, and then you have the other agent try and like help it, and so it just kind of like gives it more direction, I guess, than just bouncing things back and forth. But yeah, just a general comment. But yeah, thanks for the talk. I thought it was very interesting.
Cool. Thanks.
Yep. I'm gonna stop the recording now.